Hi everyone, I'm Xiaohua Xu from University of Texas, Austin, Institute for Geophysics. I'd like to present some follow-on work that we did near Ridgecrest, mainly targeting the deformation profiles on these small fractures and their mechanical properties. Before we really get started, I'll briefly go over our prior results and how it led to this study, showing some observations that goes to later modeling, then some implications and future work, and some take-home messages. Well, first, I would like to talk a bit on our previous work near Ridgecrest. If you want to hear more details, feel free to go to the link here for our last year's AGU talk. So back to the topic, we found a large number of lineaments or strain concentrations using in-surface gradient maps near the rupture region of the Ridgecrest earthquakes, and we called them surface fractures. After carefully processing the in-surface data, we are able to derive the vertical and horizontal deformation on these surface fractures. Interestingly, some of them goes in the direction of the prevailing tectonic stress, while some of them actually goes in the opposite direction, and we call them the prograding and retrograding fractures. They are either associated with near shallow faults or they are new ground cracks. If you take the profile on one of the fractures, you'll be able to measure the amplitude and width of the horizontal deformation. Actually, this one is averaged over a couple profiles along this surface fracture. We also derived a kinematic slip model from INSAR and GNSS data and used it to calculate the stress perturbation on these fractures. Then using this formula with the measurements from these two, we estimated the shear modulus reduction inside what we believe the fault damage zones. We did this analysis on all of them, and here are the histograms of these fractures. The displacement amplitude shows not much difference when the deformation is prograding or retrograding, but the retrograding fractures seems to generate systematically wider deformation, and thus resulted in a larger set of shear modulus ratio that makes more sense as compliant fault deformation. The prograding fractures, on the other hand, have narrow deformation, and we believe they are likely to be frictional slip. Okay, now toward this study. It all started when we are seeking a possibility on estimating all the Lamé parameters for these fault damage zones, and hoping that other than the horizontal deformation profile, the vertical profile could also help constrain a parameter. We started with this formula from Fialco et al. 2002, where U is the amplitude of vertical deformation. It is actually developed by applying the Young's modulus for normal displacement, but since the normal displacement is hard to measure, it is converted to vertical with Poisson's ratio, and here converted to shear modulus ratio with elasticity relations. They use the width term here, but in fact, it should be an effective depth term. It was presented as the width since the effective term should be largely around the similar scale. Then we did a similar analysis here using the vertical deformation, but only on the retrograding fractures that has measurable vertical and horizontal deformation. In total, there are only about 60 segments. We measured the width individually, and surprisingly, the vertical deformation showed a systematic, even wider width. The amplitude is much smaller than the horizontal as expected, but really, what does this wider deformation mean? You could sort of tell directly from these profiles. Does that indicate a more distributed volumetric damage than shear damage for these fault zones? We tend to think that's not the case. Also, this formula assumes a constant Poisson's ratio, which we know is not the case for the fault damage zones. One hypothesis we have is that maybe it's just elasticity playing its role. So we used Phoenix, a finite element computing platform, to simulate the case. We gave the fault zone 250-meter width as measured from the deformation profiles and set the surrounding crust in a 5-kilometer box. We measured the volume with a refinement getting close to the fault damage zone and a second refinement inside the damage zone. As mentioned, we calculated the strain from the slip model, converted to shear and extensional boundary conditions, then applied the shear modulus calculated from this formula with a small change here. Do note the prior one is actually an order of magnitude estimate. Since the formula is kind of derived with the fault zone extending from the top to bottom, we decided to test that scenario first. For the profile, it is done with differentiating two models, one with a changing modulus, one just homogeneous. And here are the results. The red stars are the data, and the black curves are from the model. So the model produced a horizontal deformation that matches the amplitude and width. The small mismatch here might indicate a stronger damage toward the center of the fault. There are also mismatches outside of the fault damage zone, which we will go into later. For vertical, it is kind of apparent that the wider width should be from elasticity rather than the more distributed volumetric damage. Do note that the data has an arbitrary trend removed. So what's next? Keep looking at these profiles. This mismatch outside kind of bothers us. Should this decay or deformation tell something about the fault damage zone? One key parameter we think should matter a lot is actually the depth extent of the fault damage zone. So we altered the damage zone depth and scaled the resulting deformation to the same amplitude to examine the shape of these deformation curves. And here are the results. So a smaller fault damage zone depth gives a faster decay outside of the damage zone. This sort of makes sense as the smaller size of heterogeneity makes the model goes faster back to the homogeneous model. So seemingly the 250 and the 500 meter one makes more sense, and it's actually not that loose of a constraint. As you could tell from these curves, it only starts to change more when the depth extents goes to about 5 times of the width. So you know definitely it's not going to be 1 or 2 kilometer deep. Also, what matters most is this part of the curve, considering we don't have an exact control of the trend of the data. As mentioned, this is scaled, so we could examine the shape of these curves. In fact, if no scaling is done, the amplitude will also get smaller when one assigns shallower depths, which is shown by the curves here. And likewise, it starts to drop more significantly at about 5 times the width. Thus, given a fixed shape, or in other words, decay, in order to stretch these curves back, one has to further reduce the shear modulus inside the damage zone. The other measurement we experimented on is the effect of changing fault depths on the vertical profiles. It's sort of apparent that it's a bit hard to determine just from these curves which one matches the best. But on the other hand, we shouldn't be asking too much, as the vertical amplitude is 5 times smaller than the horizontal, only like 1 to 2 millimeter, or even smaller for other profiles. And there might be north-south residual components in this decomposed vertical, even though they should be small. And when you don't scale, the amplitude drops with the smaller depths in a similar trend as the horizontal. So next, in order to match deformation amplitude and shape, we further played with the shear modulus ratio, finding an even smaller one that will stretch up the curves. What's given here is for a depth of 250 meter. If you use 500 meter, the ratio will be larger, but the overall fitting is not as good. For vertical profiles, if we just use the setup above with the best fault depths and shear modulus determined from the horizontal deformation, it's not going to fit the vertical, which is shown by the black dashed curve here. If one think a bit further, it's not hard to find that the vertical could also be controlled by the Poisson's ratio, which is linked to VPVS ratio in the fault damage zone. If we increase the p-wave velocity from the bit setup above, for example, 10% here, given a fixed shear modulus reduction, the resulting Poisson's ratio will increase to about 0.3 in the fault damage zone, and then the amplitude will match, which is shown by this black curve here. This is, in fact, not too arbitrary of a number we are using here, as it is indicated by seismic tomography, like what's shown here by Zhang et al. Near Parkfield. If you go from outside to inside the fault damage zone, the increase of VPVS ratio is largely that number. Okay, to summarize the methodology we developed here, one could calculate the local strain with a kinematic slip model derived from INSAR and GNSS. Then the fault width could be determined from the horizontal profile. We could simulate the effect of fault depths on the horizontal profiles with finite element tools like Phoenix to get the depth extent of the damage zones. Then we further tweak the shear modulus reduction to match the amplitude of the horizontal deformation. Lastly, one could find the best matching VPVS spatial change to produce the right amplitude of vertical deformation. Here are some implications and future work. The modulus reduction inferred from the model is larger than expected and within a very narrow and shallow fault zone. These are kind of constrained from the deformation profiles. When we look at the seismic tomography results, they are likely a smallest version of that. In other words, geodetic observations may provide a better constraint in that sense. Of course, this is kind of an extreme case where we know fault is quite immature, but imagine that similar cases happen next to a major fault zone that has wider damage zone and larger signals. In other words, if it works for such cases, it likely works better for larger faults. And we haven't explored the effect from a different shaped structure that will likely provide a different control on the LeMay parameters. And what if we implement a fault core that has larger reduction? Other effects like dipping faults or layered crust will also be experimented. And here are some take-home messages. So high-quality INSAR data is not talked a lot in this presentation, but in fact, it is the fundamental of everything here. All the work here is based on the deformation profiles acquired from INSAR observations. And from that, we developed a methodology to get all the LeMay parameters for the fault damage zones when there's an earthquake nearby. And what's shown here is an example that geodetic observations could individually measure VPVS changes in fault zones. And finally, getting these structures will likely help local earthquake engineering. Thanks for your attention. If you have any questions or concerns, don't hesitate to contact me.